Hello everyone, my name is Bernardo Martin-Iradi, and today I will present the multi-port berth allocation problem with speed optimization, exact methods, and a cooperative game analysis. This is joint work together with Dario, Pacino, and Stefan Ropke. The three of us are from the Technical University of Denmark. More than 80% of the global trade is carried out by sea, which means that at some point they need to go through a container terminal, like the one that you see in the picture. This amount can be also measured in number of containers, which is more than 800 million that are handled in a year in all the container terminals. And the trend, the demand seems that it's going to be increasing in the coming years. This calls for the need to increase the efficiency of the container terminals, the operations at the container terminal. Usually the operations are divided into three main areas, as the one you see in the picture, and which usually are interconnected between them. And in this presentation, we will focus on the seas and one of the most important seaside operations, which is the berth allocation. Mathematically, the operation is formulated as the berth allocation problem, where the goal is to assign incoming ships to berthing positions along the quay. We have different variants. So we have the discrete version, where we have a limited amount of berthing positions, and each of them can host at most one ship at a time, and the continuous BAP, where the ships are allowed to berth at any point along the quay, as long as they respect a safe distance between ships. We also have the static version, where it is assumed that all the ships are already at port when the planning is done, or the dynamic version of the problem, where ships can arrive during the planning process. In this presentation, we will focus on the discrete and dynamic version of the problem. A solution to this problem is usually depicted using a two-dimensional diagram, where one dimension is the quay length, in this case divided into three berthing positions, and the time or the planning horizon. Additionally, each of the berthing positions can have its own time window or the opening hours, and each of the ships is represented as a rectangle, where one dimension is the length and the other one is the handling time or processing time. Then any feasible solution will correspond to a placement of the rectangles within the decision space without overlapping. In this case, we allowed the ships to arrive before their berthing time, as in the case of the blue ships, but in this case, it needs to wait until, in this case, its position is open. In the case of the green ship, we also allow to exceed the expected finish time, but of course, this incurs in a delay. Usually, terminals do this berth allocation independently from other terminals, meaning that there is not much sharing of information between ports. This can lead to possible issues, such as the following example. Imagine that a ship is going from port A to port B, and for some congestion, it gets delayed at port A. Then the ships will need to decide basically among two options. One option is to speed up to arrive at port B on time. This, of course, means a higher fuel consumption, hence higher costs. Or option B is to propagate the delay to port B and arrive also late to port B. This will force port B to replan their berth allocation, and also the ship may face some penalty for arriving late. So the idea that we propose is in order to solve this, is to solve simultaneously the berth allocation problem in multiple ports, while additionally taking into account the sailing time between ports for the ships. This is the aim of the multi-port berth allocation problem that we present, and it was first introduced in the paper by Venturini, Iris, Kontobas, and Larsen. The idea, is to extend the berth allocation problem to multiple ports, where we solve them simultaneously. And we have an additional constraint or aspect that we need to optimize, that is the speed or the travel time between the ports. We formulate this problem as a generalized set partitioning problem, where the objective is to minimize the operational costs, both for the carriers and the terminal operators. We compute this as a weighted sum of the handling time, delay, waiting time, and fuel consumption. Each of the variables or columns will correspond to a feasible schedule for a ship, or a sequence of berthing time and positions in the ports that ship is visiting. In order to compute these variables, we use a graph representation. So we can think of a graph for each of the ships, where the nodes corresponds to a feasible berthing time at a given port and berthing position. Then we will use arcs to define the feasible travel times, depending on the range of speeds that we are allowing, that will connect berthing times at consecutive ports. So there will be at most one arc connecting 2 berthing times of consecutive ports that will correspond to the optimal speed needed to travel between these ports. The reason why there is only one optimal speed between those 2 berthing times is because it's based on the assumption that we will never speed up in order to arrive earlier. Therefore, in the picture, we only see a subset of the arcs, but if we add the rest of the arcs, basically, since it is a directed and a cyclic graph, any path from the source to the sink node will correspond to a feasible schedule or feasible column for our formulation. In this case, we're just showing an example which has the corresponding timeline in the right. The mathematical formulation, as we have mentioned, the objective is to minimize the cost of the columns. In this case, we have 2 sets of constraints. The first one is known as the set partitioning constraints. Basically ensures that there is a column for each ship chosen as part of the solution. And the second set of constraints, or set packing constraints, means that for each port, berthing position, and time instant, there is at most one column or one ship. This is done to ensure that there is no overlapping of berthing periods. Since the amount of columns can be extremely large as soon as we consider 2 or 3 ports, 3 or 4 ports, as it's in our case, we use column generation to solve the problem. We also add additional valid inequalities that we generate to tighten the bounds. And together with branching and other enhancements, we end up with the proposed branch and cut-and price. We test 3 different variants of this method, depending on the scope of the cuts that are added. First, a pure branch and price with no cuts at all. Then another variant where we only add cuts at the root node, and then the full branch and cut and price. We compare this by the MPBAP formulation that is presented in the first paper about this problem, where we solve it with Cplex. We test it on 50 different instances. 34 of them are benchmark instances from the first paper of the problem. And we generate 16 new instances that are supposed to be harder. All the instances consider between 3 or 4 ports, up to 15 berthing positions, 40 ships. We also consider 11 speed levels, and then the time windows could be tight or loose. We tested with 2 time limits, one of 5 minutes and 30 seconds, and the other one of 3 hours and 18 minutes. The time in parentheses for the case of the branch and cut and price variants, it is used in the case that optimality has not been found. Then we solve the original integer problem with all the columns generated with this 30 seconds and 18 minutes as time limit. This is used to tighten the upper bound, but even just to find the first one, if none has been found yet. The code is written in Julia, and we use Cplex 12.9 as the solver and the following machine. A summary of the performance or the results. We have the results for the 2 time limits, where we show the average optimality gap across the 50 instances for the Cplex, for the MPBAP formulation, and also the 3 variants of the branch and cut and price. We could see that the proposed methods are able to achieve quite tight optimality gaps within the 5 minutes already, and all of them are able to find more optimal solutions than Cplex in more than 3 hours. One of the reasons for this is the tight root node bound that we achieve, where we basically by solving the root node, we are able to find the gaps of under 0.1% in average in 25 seconds. Of course, this problem is based on a high level of collaboration, which means that some carriers or terminal operators may be a bit reticent or to engage in this type of collaboration, especially if the overall optimal solution seems different than what they are used to plan, or that seems that they can not benefit them. So in order to incentivize the collaboration, we present a cooperative game where the players are the carriers, 3 carriers in this case, and 4 terminals, 3 or 4 terminals, depending on the instance. And the goal is to find a cost allocation of the solution to the problem, where the costs are basically distributed efficiently, so that each of the players can see that they can achieve savings compared to its basically a standalone cost. There are multiple ways of computing this cost allocation. We test 2 of them, the Shapley value and the equal profit method. Both of them are quite simple methods to compute. They only require to calculate the cost of all the sub-coalitions, which in this case, we compute using a fix and optimize heuristic. That for the sake of time, I will not go into detail. So an overview of the solution or of the cooperative game. We divide them into 2 different tables, depending one for the instances with 3 terminals and the other one with 4 terminals. So it's just an additional player in the table on the right. But the insights are pretty similar between both of them. We should notice that all instances have a non-empty core, meaning that we are able to find core solutions for all the instances. A core solution can be seen as the one where the solution or for the grand coalition or where everyone collaborates is the most attractive scenario for any player, which is good. And in terms of the results, we can see that all of the players, of course, are able to find savings with both methods. For example, Shapley value tends to balance the absolute cost, whereas the equal profit method tends to balance more the relative savings. There is no better or worse solution in this case. It's just it's more to highlight that there could be many ways of distributing these savings efficiently while everyone benefiting at the same time. So as a conclusion, we present a good performing algorithm. It's able to find high quality solutions in short computational times, which can be seen attractive from a planning point of view. The graph representations for the ship schedules allow us to accommodate additional operational constraints easily. And then the cooperative game shows that there could be win-win situations for both carriers and terminal operators of engaging in this type of collaborative logistics. And this may raise also the question of who may be willing to apply this type of model. And we envision that this could be applied, for example, by third-party companies that currently offer planning software for both carriers and terminal operators and already have access to some of the data that is required for solving this problem. As a future research, we are currently working on the continuous version of the problem and improving aspects such as the branching strategy. And future research could be to include additional aspects such as transshipments or external ships, and also integrating it further with other operations at the container terminal, such as the key crane assignment. Thank you for your attention, and I'm willing to answer any questions you may have.